Here we want to know the force only in 3 of the members, BC, CF, and FE. So with the force in BC, CF, and I'll call it EF to maintain the alphabetical order that I use in these problems. Depending on which members we want to know the force in, we might have to go through a lot of pin diagrams to get there. In this case, we want FE, CF, and BC, which are kind of in the middle of the truss here. We're going to segment or section out this truss and analyze basically a subsection of the entire structure. Now this one's set up nicely. We want to know the force in BC, CF, and BC. So the idea here is, can we make one continuous cut through the structure, close it in on itself, and then keep everything on one side or the other of our cut? We have a pin at G, we have a pin at A. So how many external reactions would we have?
4.
Right, there's going to be 4, a GX, a GY, an AX, and AY. There's 4 external reactions, meaning that this is a statically indeterminate structure. So no matter which method we want to use, I recommend we would skip an external free body diagram anyway. And like with the method of joints, we could go right and jump in at D to E to C, or to C to E, either way. With method of section, same idea. Skip over that external diagram and jump right to a section cut as our first move. So here, if I take everything to the left of this cut, I will be including G and A in that picture, meaning I would need to include what is AX, AY, GX, and GY, as well as the force in all of the members that I'm cutting through. So if I made this cut without an external free body diagram, I'm going to be introducing 7 unknowns right away in one picture. And I won't have enough equations to cover that. However, if I make this cut and I keep everything to the right-hand side, then I don't have any supports to the right of this cut. I'll only have the 3 forces in the members that I've cut through. So let's see what that free body diagram looks like when I take a section cut through these 3 members. Again, as a rule of thumb, we don't want to make a cut that goes through more than 3 members. Sometimes that is useful to us, but usually that's going to make the math a little bit harder to get through. So I can cut through 3 members, and they're the 3 members I'm interested in finding the forces in. So my free body diagram, potentially I could have multiple. I want to copy exactly all of the members that I did not cut through. Again, if I'm keeping everything to the right of my cut, that means that members CE, DE, and CD are going to be exactly the same as they are in this picture. So first I just copy those. Then I want to include the parts of the structure that I'm cutting through, but they are cut off. So basically where I'm cutting through them, because I'm now separating this structure from the rest of it, it has now exposed what the internal forces were that were keeping the structure together, that now that they're cut apart, I'm able to see. So I've cut through member EF, so I can see what the force in EF is. I cut through CF, so I'm now able to see the force in CF. And BC, the same thing. And CF, I'm going to know, is going from C to F, so that is going to be a 1-1 root 2 triangle, or this is a 45-degree angle, if I wanted to do it with angles there. I also have to copy exactly all of the external forces and all of the supports in the pieces of the truss that were kept. So like at C, I have this 600-pound force. And at D, I have an 800-pound force. This picture does not include B, so I can't see that 600-pound force to the left of my cut. And this picture does not have A or G in it, so this picture doesn't see those supports that are happening. If I look at what I'm left with now in taking everything to the right of that cut, the only unknowns I have to the right of the cut were these three internal forces that I now see since I cut through it. If I took the other side of the picture, I would still have these three internal forces, but I would also have four unknowns from A and from G. So in this case, I can efficiently find the three unknowns I'm looking for, as they're all going to appear in my single free body diagram. So from one picture and the three equations, I'm going to be able to find the three unknowns that I'm interested in. I can take this and I can write the equilibrium equations based on the section cut that I've just made. So I can take two forces, and I can take the moment around a single point. And I'll label what those points are also in my free body diagram. Looking at the section cut, what equation can I start with that's going to make the solution easier to start? I do sum of forces y. In this case, CF is the only force with a y component. So sum of forces of y will give me this answer right away. Right. Alternatively, in this one, if I took the moment at C, then EF would be the only unknown. So that would also be a good place to start. The worst place to start, only in terms of the order of doing things, would be sum of forces x, since three of them are going to have components in the x direction. So actually, sum of forces x, I'll choose to do last. But I want to keep reiterating, the order really doesn't matter. You just, as long as you have the equations you need, then you could decide later in what order you want to solve them. But since we're doing this by hand, I'll start with sum of forces y in my picture of my sectioned free body diagram. I have the applied forces down, minus 600, minus 800. And I have a component of CF pointing up, 1 over root 2 FCF. So starting with that first equation, FCF is the only thing I don't know. So I can find FCF to be 1,980 pounds. And positive, so it's tension. So we could go to the moments next, because that will give us a different unknown right away as our second equation. So if I take the sum of moments around C, then FEF will be the only thing that we don't know, and we can solve that right away. So in the moments around C, the 600 pounds passes through point C, FCF passes through C, FBC passes through C. So these three are eliminated when I take the sum of moments around C. So I'll just be left with this 800 pounds and FEF. Again, these equations are derived only from the picture, and then later I can put in any numerical values that I have. So according to the picture, I'm going to have a moment caused by FEF that is 4 feet away, and in the picture that's going to be counterclockwise around C. So that will be a positive 4 times FEF. And then 4 feet away from, or the 800 pounds is 4 feet away from C. That's creating a clockwise moment around C. So I'll have a minus 4 times 800. From equation 2, FEF is the only thing I don't know. Actually, I can cancel out these 4s. So FEF, I should get positive 800 pounds, and then that too is going to be in tension. My final equation, I take sum of forces in the x direction. I have negative FEF, which I know. negative FBC, which I still don't know. And also in the negative x direction, 1 over root 2 times FCF, which I know from the first equation. FEF I know, FCF I know, so the only remaining unknown in equation 3 is FBC. So plugging in 1980 for CF, 800 for EF, I find that FBC is a negative 2200. Right? Meaning that FBC is in compression since we got a negative value there. I should point out also, I'm making the same assumptions about tension that I did for the method of joints. So always from the cut surface, I'm drawing the arrow coming out of that, and that is assuming tension. If the arrow were pointing towards the surface of the cut, then I would be assuming compression. So just like in method of joints, a positive value, as long as I always use that same assumption up there, positive is going to still be telling me tension, and negative is still going to be telling me compression.